Guru, start.
Good evening, everyone. Welcome to the webinar on NASA small spacecraft technology and Kepler missions. So, good evening from India, Mr. Roger Hunter, and good morning from California. And thank you for accepting our invitation. So, I would like to introduce today's speaker. It's my privilege. I'm honored to introduce Mr. Roger Hunter. He is the project manager for NASA's Kepler missions, which is one of the prestigious programs, the first mission capable of finding potentially habited planets in the Milky Way galaxy outside our solar system. So it has a lot of interest among the scientific community specific to finding out the habitats outside the solar system. Prior to joining NASA, Roger also served with Boeing, and he has managed about 250 Boeing engineers, and they have successfully steered the GPS, that is Global Positioning System, satellite constellation, and also he has served GPS command and control system at Air Force. Roger also served in various capacities at US Air Force and retired after 22 years of service. He had successfully executed assignments with Headquarters, US Air Force Space Command, and Headquarters, US Air Force at Pentagon. So Roger Hunter is an eminent speaker and also space enthusiast. And Mr. Roger Hunter, over to you. And thanks for accepting our invitation. And I'm sure next 1 hour we are going to see a lot of insights about Kepler missions.
Thank you so much for that kind introduction, and good morning again from California. I have two subjects primarily to discuss today, and that is my job as the program manager for the NASA Small Spacecraft Technology Program. And as mentioned in the introduction, at the end of this, I will touch on the NASA Kepler mission, for which I was a program manager for a number of years. And I will highlight a couple of upcoming activities also at the end that NASA is going to be engaging in the very near future. So let's talk about small spacecraft technology activities within NASA. And we use small spacecraft to demonstrate new technologies that could be used for future science or exploration missions. And that is a job I focus in mostly on the left. And that includes developing in technologies as well as subsystems that those technologies and subsystems, once matured out of the laboratory, can be instantiated into those two other missions that you see on the right, whether it's exploration or science. So I will be focusing most of this talk on the column on the left, which is on space technology. And this is the objectives of my office, and it's primarily to expand our capabilities. As you know, the electronics and technology revolution has brought us to the point where we have so many capabilities just in our hands. And we're taking advantage of this rapid advancement in the electronics and technology revolution to put these into spacecraft that are sometimes as small as a tissue box or a loaf of bread. And you can see one on the right there, and I'll be talking about that one shortly. But the real objectives is to let's lower the cost of these missions and also reduce the time that it takes for us to build a spacecraft and get it into orbit and conduct this new mission. We're also looking at the use of small spacecraft technologies that could enable and demonstrate new mission architectures, such as swarms of small spacecraft that could be oriented towards a target of interest like an asteroid or a moon. And one of the things that we are working on more recently is trying to improve the capabilities of these small spacecraft to enhance them so that they can be used for new destinations. Most small spacecraft you see today are used in low Earth orbit. But we are now getting to the point where we're now sending these not just to the moon, but also out to Mars. And we also think that these could be used to augment existing assets and also future missions in a supporting role. So where do we get our technology development? And as you might expect, they come from the normal pipelines with either university partnerships or small businesses. Sometimes we engage in public-private partnerships with small and large companies. As we develop those technologies, then we put them onto these demonstration missions to validate that they're working properly in the rigorous space environment. This is an example. This summary chart here shows you how we have been participating with universities across the United States We've been trying to do this on an annual basis, and we award millions of dollars to different universities on the ideas that they bring forward to us when we solicit for new ideas that will enhance the capability of our small spacecraft, which could then be used later for one of those sites or exploration missions. And the results have been very rewarding. We have awarded over the last 5 years about $27 million in these grants. And this money goes a long way at these universities. They have grad students working on these and professors that are mentoring them. And you can see the results is that we've had a number of good results, or a number of good technology developments coming from these different universities, particularly when we pair them with a NASA center every time to offer them guidance and support and mentorship as that university is developing the technology that is going to enable future NASA missions. This is an example of a recent class, and these are the final ones that were selected. And you can see that there are different universities that are represented here. Of course, these range from anywhere to like University of Boulder, Colorado, and their team with JPL and some others from the state of California. But we also have other universities coming from San Diego State, Utah State, and University of Illinois Urbana-Champaign. And if you look down the list on the left of the technologies they're developing, they're sort of along the lines of what you might expect we would be trying to push on to enable our small spacecraft to move beyond low Earth orbit and into the cislunar space and then into planetary space. Of course, many of these are going to be communications oriented. Some will be navigation oriented. Some are going to be propulsion oriented. Some, if you look at the one that's sort of in the middle there, called an additively manufactured deployable radiator, that one is going to be oriented toward enabling new sensors that would perhaps need cooling, because you're getting into the area where you're generating a lot of power, particularly if we start putting more power on the spacecraft. So there's a wide range of technologies that we are pushing on with the universities over the last 5 years, and that we'll continue to push on. And of course, as I mentioned earlier, these are going to be oriented towards propulsion, power, communications, and processing. So that's where we're headed with a number of these small technologies. And now I'd like to talk about just some recently completed missions, just to give you a flavor of what we're doing. And you can see a hand or fingers in each one of these to give you a perspective on size. These two spacecraft, the integrated solar array and reflector array antenna, and the one on the right, the optical communications and sensor demonstration, were oriented towards improving our capabilities for small spacecraft in the communications area. You can see that flat panel array antenna on the spacecraft on the left, and that was invented at the Jet Propulsion Laboratory. And that particular spacecraft was demonstrating the use of Ka-band communications for the first time ever on a very small spacecraft. We had used Ka-band communications before on a much larger spacecraft, and coincidentally, that happened to be on Kepler, the mission that I ran for a number of years. There was an opportunity that I will talk about in a moment. Right before we launched that spacecraft on the left, the Aerospace Corporation recognized that we had some additional space on board the spacecraft, and they wanted to also add in an additional sensor package, a multispectral imager that they were building. And we allowed that, but we also provided that capability or that opportunity for them only after we had completed the primary demonstration of the spacecraft on the left, which was to show a spacecraft doing Ka-band communications from a 3U size spacecraft to low Earth orbit. And that one achieved 100 megabits per second. I'll come back to that one in a moment. The one on the right, you see one of a pair. So it's a twin or a duo set of spacecraft. Each one is just like the other one. And this one was going to demonstrate laser or optical communications from a very small spacecraft, also from low Earth orbit. And the intent here was to show that we could equip small spacecraft with laser comm and make them successful, and also up the data rate transmission over and what we normally have had for spacecraft of this size in the past. And this one was demonstrating 200 megabits per second, and I will show you a demonstration here momentarily. But I want to talk about the spacecraft on the left and the multispectral imager that we put inside. You may be familiar with the horrible forest fires that California had about a year and a half ago that were burning out of control in Northern California. And after we had completed the demonstration of the Ka-band communications of the spacecraft on the left, if you see my cursor moving around the end of the spacecraft, that was where we had placed that 1U size multispectral imager that had capability in both visible, long-wave infrared, and short-wave infrared. And after we finished the primary objectives of the spacecraft, we turned the camera on and we started imaging things. And I want to show you some images that this one little multispectral imager, which is about 10 by 10 by 10 centimeters in volume, was able to see from a height of about 450 kilometers above the Earth's surface. And this campfire, they called it, it was near Chico, California, a few hundred miles north of where I live. You can see the outlines of this, and you could see it in the visible. You could also see a composite photograph, and that was basically merged in the high dynamic range and high gain. And then you could also see this in the long wave infrared. But if you can see my cursor on the photograph on the far left, and I'm circling the area in the middle of that, that was a town known as Paradise. And it was wiped off the face of the earth by this large fire. And it was kind of sobering to see this as these images came in. And we were pleased with the performance of the spacecraft, but of course, we were obviously saddened by the loss of life and the loss of property that this fire caused. And it was intriguing that we could fly up over this at night and we could see the fires raging inside the town of Paradise and the smoldering embers of that town. So I want to show you a demonstration of the optical communications and sensor demonstration. And this was the two spacecraft I just mentioned, and it's just an animation that shows their deployment. This spacecraft did have propulsion on board, and you can see it sort of spitting like a 2-year-old child. The propellant was water, and we would just simply heat it up like a little steam engine and putter around each other. But the secondary objective, after you just saw the laser comm igniting, was to show that the spacecraft could also demonstrate proximity operations around each other. We had these spacecraft as far apart as 476 kilometers and as close as 6 meters. Of course, that animation is is sped up quite a bit so that we could demonstrate to you just how they're moving. We did something interesting using both of these spacecraft and the first spacecraft I talk about called ICERA. After both missions were complete with their primary objectives of demonstrating Ka-band communications for the first spacecraft, and then optical communications for the second spacecraft, and also the second pair of spacecraft finishing off the proximity operations demonstration, we took the opportunity to see if we could do something that involved all three spacecraft. And I want to show you something that we found really interesting. And I'm going to let you look at this image before I run the animation here. If you look right here, and then when I turn on the animation, you will see this move across your field of view here from left to right, going from about the 10 o'clock to 4 o'clock position. That is not a UFO. That is a star radiating very hotly in IR, and the Cumulus multispectral imager is what we call it. That was on the ICERA spacecraft. We had turned it on its side and we were staring in this area. In this area, what you'll see light up when I start the animation is the laser from the optical communications and sensor demonstration. And these spacecraft were separated by about 2,200 kilometers, and we were able to track and point at the Cumulus sensor on board that ICERA spacecraft. Turn on animation, you see, like I said, this star moving across, but you're right here in the very middle, you see the laser light up for the OCSD, and there it goes. This course animation is sped up quite a bit, but we were able to sweep the laser across the focal plane of the cumulus or multispectral imager that we had placed on ICERA. And let me see if I can run that one more time for you so that you can see it if you didn't catch it last time. And right there in the middle, you see it. There was, we thought this was kind of cool. And so we actually put this animation out on the NASA main Twitter feed. And we got a lot of great comments, many words were said, cool, this is interesting. We've never seen this before, but we were rather amused that the Flat Earth Society also said this was fake imagery from NASA because they were looking at this limb of the Earth here. And they said, the Earth is flat, it's not round. And of course, we had a little bit of fun just teasing them after we put this, this Twitter feed out there. Now I'd like to switch gears on you just a moment and talk about the upcoming small spacecraft technology demonstrations that we have planned in the not too distant future. The two that you see on this page, one on the left is called the Pathfinder Technology Demonstrator. That's a 6U, about a 30 by 20 by 10 centimeter size spacecraft, half of which is reserved for a new technology payload that we want to demonstrate. And there's a list of those at the bottom of this chart. Some of these are propulsion-based, like you see the first one is from a company called TUI, and it's called the Hydros Water-Based Thruster. There's another improvement in ADCS, or Attitude Determination and Control Systems. This one is called HyperExact, provided by the Blue Canyon Company. And we're also working on another high bandwidth laser communications activity with the organization within NASA, but also with the Massachusetts Institute of Technology Lincoln Labs group. And there are some other activities associated with another reflector array antenna, and then something, the number 5 called LISA-T. That is, if you imagine someone who can do origami, this is a lightweight integrated solar array and transceiver that stows into just 1 U of space in that 6U size spacecraft. And when it deploys, it puts out about 600 watts of power for a very small spacecraft, which is what I find kind of interesting. And that one is on schedule to be demonstrated in not too distant future as well. So that covers PTD, or the Pathfinder Technology Demonstrator. The one you see on the right, the CPOD, or CubeSat for Proximity Operators Demonstration, 2 spacecraft you see that are approaching each other and they're about to dock. And so that's what we're essentially going to be demonstrating with this mission. There's a cold gas propulsion system on board, and there's visible and infrared imagers, and there's GPS, and there's a laser rangefinder, and this thing is loaded with technology. And once they're put on orbit, they will separate up to a distance, and then they are turned on, they're told to find each other, and then they autonomously conduct rendezvous and proximity operations and then dock with each other. This is another array of technology demonstration missions that we have lined up that are coming in a very near future. The one on the left, and I'll go with these from left to right, VREX, which is just a 3 1U size spacecraft that we're going to be demonstrating topology recovery and just, you know, autonomous low power, low cost spacecraft ranging between each other. And we actually did this very fast, and from start to end it's been less than a year, and we hope to launch this by the end of the year, COVID-19 permitting, because we're slowly also coming back to work at NASA Ames Research Center where I work. The second one you see here is a follow-on to the optical communications and sensor demonstration that I mentioned earlier. OCSD was demonstrating laser from satellite to ground. With this one, we're going to demonstrate inter-satellite laser communications between 2 spacecraft that are also about 3U in size. And even though it doesn't have quite the data rate as OCSD does, but this one, as I mentioned, is another advance in the use of optical communications by small spacecraft on orbit. And they'll be able to transmit data rates of up to 20 megabits per second at a range of almost 600 kilometers. The one you see as number 3 here, we call it the Advanced Composites-Based Solar Cell System. This is going to be another solar cell that NASA is building as a technology demonstrator. And given lighting conditions in the early evening hours, you'll probably be able to see this from space once we get it on orbit. That's about 81 square meters of sail material that you see in this demonstration. And in the middle is the spacecraft, the 12U spacecraft that we pack all of this sailing material into. The technology we're demonstrating here is not the sail material itself, it's these new composite booms, because when you get a large solar cell on orbit and you're using these metallic booms, they start warping and twisting. And so we invented this new composite-based material that's going to be used to unfurl the sail on orbit. And then we will demonstrate that these composite booms can basically unfurl properly, and then we'll be able to control them like a weather vane and start moving this thing around a little bit. And that will be an advancement in solar cell technologies. The one on the right, this is a demonstration of a swarm of spacecraft. The picture just shows 3, but there will be 4 spacecraft in this swarm. They're all about 6U in size, and they're going to show 4 spacecraft cooperating, collaborating, and working with each other so that they can do ad hoc development or configuration of communications networks between the 4 spacecraft, and also do what we call, it's called formation flight, but actually it's called cluster flight management. All 4 spacecraft are intended to stay within RF range of each other. And of course, in low Earth orbit, you're subjected to the vagaries of the solar wind. And if 3 of the spacecraft, for example, start detecting that the 4 spacecraft in the flight starts moving further out of range, then the 3 tell it to move back. So we're demonstrating this autonomous operations on orbit with these 4 spacecraft, and also the fact that these 4 spacecraft can also collaborate and cooperate with each other. And it's going to be launching in a little over a year and a half from now. Here are 2 spacecraft that also are going to be launching next year. I'll talk about the one on the right first, and this is called Capstone. As NASA pivots toward returning to the moon with a sustained presence, we intend to also put a new space station that's going to be orbiting around in the cislunar space. And there's an orbit, a very special one, called the near rectilinear halo orbit. And if the students are interested in this, you'll be able to go check out some YouTube animations for that NRHO, or near rectilinear halo orbit. No one has ever flown in an orbit before, and we want to verify the mathematical models are as predicted. So we're building this spacecraft called Capstone, which will be placed into that orbit that Gateway would occupy at some time in a not too distant future. And this spacecraft is a little over 12U in size, and it's going to be launched with its own rocket. We bought them their own rocket with our Rocket Lab for launch in early of next year. I think it's March is when this is scheduled to go. But it's going to be doing some ranging between our deep space network on the surface of the Earth, and also a spacecraft that is in orbit around the moon today that's been there for almost 11 years, called the Lunar Reconnaissance Orbiter. And it's going to be ranging between those 2 entities so that it can help better characterize this near rectilinear halo orbit. And that's going to, as I may have mentioned, will launch in, I think, in March of next year. Now, the one on the left here is called Lunar Flashlight. And that's about a 6U size spacecraft, and also packed with instruments. But the primary instrument is a laser payload. And that laser payload would operate in 4 different wavelengths, mostly in the near infrared region. And as it's orbiting the moon, it's going to be lasing those darkest craters to see if we can measure and quantify the distribution of, as you can see in the wording there, the surface ice deposits, particularly in the lunar South Pole area. As we illuminate the craters, of course, we collect that reflection back up on the spacecraft, and we can measure the reflection of regolith versus water ice deposits. And that will give us an indication of the prevalence of water ice on the moon. We proved almost a decade ago that there is water ice on the moon with another mission called LCROSS. If you're keen on learning about this detection of water on the moon, you can look at that mission called LCROSS. But this one, Lunar Flashlight, a very small spacecraft, is going to be helping us determine more of the prevalence of water on the moon. So this is just basically a summary of that information as I get ready to switch topics with you. But this is why we have a small spacecraft technology arena within NASA, and is to improve the capabilities of small spacecraft so that they can be used by themselves, perhaps in the future for science and exploration missions, or they could provide add-ons or escorts to other larger missions. An example of that would have been the InSight lander when it went to Mars. It was escorted by 2 of these CubeSats, which actually relayed the entry, descent, and landing operations of the InSight lander onto the Martian surface as the 2 CubeSats, known as Marco, were conducting a flyby of the Martian surface simultaneously. So this is the summary of the small spacecraft technology development area that I wanted to chat with you about today. And this is a schedule of all of those missions I've been talking about, and most of them, as you can see, a lot are in FY21 and FY22, and we have some more coming up afterwards. Now I'd like to switch gears with you. In the introduction, it was mentioned I was the program manager for the Kepler mission for quite some time, and that spacecraft was decommissioned in November of 2018, and it was launched in March of 2009. So it spent 9.5 years looking for planets within our Milky Way galaxy, and the results were very satisfying. I think we exceeded our expectations with the detections that were made and announced by this mission. I think it's one of the more noble missions that NASA has conducted. It may not be the same as Apollo, but in its own niche, it helps us have a better understanding of what is out there from the perspective of what is the menagerie of planets that exist within our galaxy. So I would like to spend some time talking with you about results, but this chart here depicts the original field of view of Kepler as it's looking through the Cygnus constellation and also near Vega and Lyra. And the checkerboard pattern you see there is basically a footprint of the photometer that was on board Kepler. And that photometer was the most precise camera that at the time that NASA had ever put onto a space telescope. And that's a really large field of view compared to most ground telescopes. It's many times larger, but we needed a large collection field so that we could do a statistical analysis of the planets that are out there. And as I mentioned earlier, the results were fascinating. Let's talk about that for just a moment. These 3 yellow dots you see here are the known planets that had been detected by other means before Kepler was launched. And this was before we started the planet search with Kepler after its launch in March of 2009. We finished the commissioning of the spacecraft in just a little over a month, and then we began hunting planets. And within 4 years, this is what we found in that field of view. I mean, there was over 4,700 planet candidates, and these dots represent basically the planets were everywhere. And we sort of tried to characterize and categorize them for you from Earth size all the way up to planets that far exceeded the size of Jupiter. We found planets as small as the size of our moon, but of course, we were looking for the Earth-sized planets in the habitable zone. And I just pulled this off of the NASA website recently, and I draw your attention to the box on the top, particularly the box in the middle that says candidates and confirmed planets in the so-called habitable zone. And there's 361. We're in the process of confirming those, and I think several dozen have been confirmed already. But there are, I almost said, almost 5,000 planets in that original field of view as Kepler was looking for these planets. And the nature builds solar systems as nature wants to build them. Our solar system isn't necessarily a cookie cutter for all of the different types of planetary systems that we saw out there, if you want to call them solar systems. And they run a gamut. They're just a wide variety of the way nature builds planetary systems or solar systems. At the fourth, there's one thing I would like to remind you of. And if you students become a program manager or a chief engineer at some time on your future space mission, if that's where you're headed, I want to mention something to you. You're going to encounter issues that happen sometime on your spacecraft, and this is what happened with us on Kepler. Matter of fact, by the fourth year, we had suffered sequentially a reaction wheel failure or a gyroscope failure in the third year and also the fourth year, and that's where the K2 mission came in. For almost a year, we sat figuring out how to recover the spacecraft because you needed 3 reaction wheels to point accurately enough to detect planets. And an enterprising young engineer found out that even with 2 reaction wheels left, you could use the solar wind as a balancing tool to help you still point the spacecraft accurately enough that you could detect planets. We could not look at the original field of view because you needed 3 reaction wheels to do that. But with 2 reaction wheels and a solar wind, we were still able to repurpose Kepler into its part 2 mission or sequential mission, and looking for planets while we probed around the ecliptic plane. And this is what we found. We were able to still continue looking for planets. Now, we had to move the spacecraft every 86 to 87 days and repoint it because we had to avoid sunlight getting into the barrel of the spacecraft. And if you're intrigued by that particular recovery, there's a couple of papers that are out there available to talk about how Kepler was repurposed from its original field of view to a different sets of field of view because an enterprising engineer figured out how to use a solar wind with remaining reaction wheels on Kepler to make this mission still productive and find even more planets. I thought it was intriguing. It was just an amazing use of a spacecraft that had been crippled in other ways. This is a summary of all the planets that are out there, and this is what it adds in the uses or the results, I should say, of another follow-on mission called TESS. Kepler was looking far and deep into the galaxy, whereas TESS was looking more into our own stellar neighborhood. And TESS has continued to find planets as well, but the results are basically affirming that what we believed in the first place, that our solar system isn't necessarily unique. We are, as Carl Sagan once put it, a mote of dust hanging around some nondescript star in just a far off part of the galaxy. Planets far outnumber the stars. And as a matter of fact, when we talk about the results of where we have come with Kepler, there's 2 things that we remind audiences of, and it is this. Go outside at night, get away from your city lights, look up into the sky, and every 5th star you count has a habitable zone planet. So 1 out of Earth size. Every 5th star has an Earth size habitable zone planet. And every star hosts at least 1 planet. So planets far outnumber the stars, and the potential Earths that are out there are quite an astonishing number. Kepler, as I mentioned, was decommissioned back in November 2018. This is one of the last images we took. We intentionally turned Kepler towards the Earth, and this is from a distance of about 96 million miles. Of course, it's such a precise photometer. We lit up some of the circuitry on the photometer, and you can see the brightness here that's been illuminated from the planet Earth. And this is one of the last images we took, and it's sort of a goodbye photograph for Kepler, and has now been committed to the depths of space. I have a challenge for the students that are with us today. Kepler's orbit is a heliocentric orbit just like Earth. It takes us 365 days to go around the sun, and it takes Kepler about 371 days. So it's like 2 runners going around a racetrack, and 1 runner is slower. eventually, as they continue on the racetrack, the faster runner will lap the slower runner. So one day, Earth is going to go right by Kepler again, and that is in September of 2060. If some enterprising student is on the talk today, I would commend you to work with your colleagues to see if you could go up and retrieve the spacecraft and bring it back and put it in the Smithsonian, because I think it's a fundamental space telescope that has fundamentally changed our understanding of the galaxy. Now I'd like to switch gears because there's been a lot of excitement about some recent events, and this is the Falcon 9 rocket on the left, has the Crew Dragon capsule on top. And it was one of those beautiful early morning photographs of the launch before it happened. And of course, the right is a depiction of the spacecraft that's just nearing the International Space Station. The Crew Dragon is still attached to the International Space Station. The astronauts are still there. They can stay up to 210 days. I don't know what their timeline is for this experiment, and also verification that this Crew Dragon works properly. But they were coming back in a not too distant future, but I thought it was an exciting event if you were able to catch the launch. By the way, if you've never been to a launch, I would recommend it as a bucket list item. It's something to really experience because it is exciting, and you get, not only do you get to see something leaving the surface of the Earth, but you also get to hear the rumble, that rocket sound. And if the rocket's big enough, you perhaps get to feel some subsonic waves passing through you if you're close enough to the launch site. I just want to give you a perspective on a couple of things. This is astronaut John Glenn as he was getting into the Mercury capsule back in the early 60s. He was the second American to make it into space, and he was the first American to actually orbit the Earth. Alan Shepard was the first American in space, but his flight was suborbital. And just show you how small the Mercury capsule is as they were cramming him into that thing. You could hardly move in it once you got into it. And this represents an evolution of where we're going in space. And you can see the cockpit for Apollo, the cockpit for a space shuttle launch. And then you see this rather futuristic looking capsule here, Crew Dragon on the bottom. And if you want another comparison, you can see Crew Dragon here on the right. That's Elon. And you can see Soyuz on the left with the cosmonauts crammed into the Soyuz capsule. So you can see there's been also an advancement in the way we're building manned spaceships as opposed to where we did them back in the early 60s. And give you just a snapshot of things that are coming up. There's another capsule being built for a crewed flight up to the International Space Station. There's a picture of that on the left. That one's being built by Boeing. And the one on the right is another one. And this one is not man-rated. This one is cargo-rated only. And this one is built for NASA by a company called Sierra Nevada, and it's called Dream Chaser. And it looks like a miniature version, if you will, of the shuttle. And this one is also going to be launched in 2021 and represents another capability for shuttling cargo back and forth between the International Space Station. But these are coming up in the not too distant future, with the one on the left, I think, going up later this year, and Dream Chaser, the one on the right, launching in sometime in 2021. Another event I like if you're into interplanetary discovery, our next rover to Mars launches next month on July 17. And you can see an artist's depiction of that rover in the background. But this is the first time that we're actually going to fly a man-made object through the atmosphere of another planet. And this rover is going to have a helicopter attached to it. And I found it interesting that the control box for the helicopter looks to me a lot like a CubeSat. But this is a technology demonstrator. It is not really meant to conduct science, but it wants to prove that we can actually fly a helicopter or some kind of airfoil through the atmosphere of another planet as part of a potential capability that we would want to use for follow-on missions in which we would want to fly through the atmospheres of a moon or another planet and actually do real science. And there's a short video on this that I would like to share with you. And this gives you an example of this helicopter flying through the Martian atmosphere. And this shows you first it's being deployed from the rover, and the rover backs away from it to some. And we actually will train the cameras onto the helicopter as it is then commanded to lift off from the Martian surface. It has solar power, and you can see the little solar cells on top. And this is not going to fly too far out of range of the rover itself, but it's going to be one of the first demonstrations that we conduct with the rover, and you're going to fly short distances. There is going to be some terrain mapping or some photographs that we'll take of the surface that we will then perhaps use that for a follow-on mission. If you fly helicopters or other flying devices through the atmospheres of Mars in the future, or perhaps on another moon. And so that rover launches on July 17, and it takes, of course, about 7 months to cruise out to Mars. But there's one other thing I would like to point out that's also on this rover. And you see at the bottom of the rover here, this is a picture from earlier last month as the rover is going through its final installation and checkout phases at Kennedy Space Center before it's loaded on top of the rocket. You see these little tubiles there. Those are going to be used to collect and cache different samples from the Martian surface. And they will be cached at a particular place on Mars. And this rover is going to Jezero Crater. And those tubiles you see there are going to have collections of soil that we think may have had fossilized remains of some sort of indication of life in the past. We don't know for sure. We want to see. We think there has been. And then these tubiles will be cached on the Martian surface. Then a future mission will go to Mars, retrieve those tubiles, those cache collection tubes you see there, and then bring them back to Earth. So I wanted to share those with you. Those are some upcoming missions that I think are pretty exciting for NASA. And there's one other one that I would like to bring to your attention. And this spacecraft called OSIRIS-REx is orbiting an asteroid today called Bennu. And on October 20th of this year, this spacecraft, which has been orbiting this asteroid for quite some time, is going to do a touch and go on the surface of that asteroid. And we're going to collect a soil sample with this device you see here at the very end, if you can see my cursor moving around it, as it slowly descends to the surface of the asteroid. And we'll use the momentum of the spacecraft to lightly touch the asteroid. And when it stays in contact with the asteroid just for a few seconds, we'll blow a cold gas into that collection thing so that we can blow some pebbles and dust up into that collection device and then put it into this return capsule here. And then after October 20th, we will back away from this asteroid for just a short distance, make sure we've collected enough of the material that we like to bring back to Earth, and then we will turn and burn toward the Earth in March of next year, and it takes about 2.5 years to get back. So that's another mission I think you may find interesting to follow later this year. So we have, in summary, a couple more capabilities that show one, another capsule capable of crewed launch up to the International Space Station. That's the Boeing Starliner. The Sierra Nevada Dream Chaser will launch in early next year, which shows another capability to shuttle cargo back and forth between the International Space Station. And then the next rover to Mars launches next month, and to demonstrate a helicopter and also the caching of a collection of soil samples from Mars, which will be then retrieved by some future mission going to Mars. And then, of course, we have this mission, OSIRIS-REx, orbiting Bennu, which is going to collect a sample later this year from the surface of the asteroid and return to Earth. And this is just a spot on the Bennu that we'll be collecting that from. And I think that's what I want to present to you today. I know that's a lot of material to digest in my 45 minutes. And I think we have time now for some questions. And so I will rely on the proctors to help me out with those questions.
Yes, thank you, Mr. Rover, for the brief introduction and then explaining about what are the missions that are specific to Kepler and small spacecraft missions and findings of these Kepler missions and so on. There are a lot of interesting questions specific to, of course, in general to space exploration, and then specific to what the things that we have discussed here. So I'll start with the most relevant questions, and then we'll take the conversation forward. Is it fine?
Yes, yes, please.
Yeah. The question is that how big is the space? So I think it is most generic question. So for the kids, how big is the space, and what dimensions do we see space as a entity?
Well, the size of the universe for what we call the observable universe is how far have our telescopes reached so far, and it's about 13.7 billion light years across. That's what we have been able to discern so far, and we are always careful with that because that's what we can see. What lies beyond, we don't know. Is there an edge to the universe? That's a riddle, and there's some puzzling things about the universe besides its size. It's so immense. To me, it's incomprehensible, particularly when you think about terms of 13.7 billion light years. The farthest object that we have sent into deep space, and we have sent 5 spaceships now to the stars, if you want to think of it in that terms: Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and now New Horizons, which was sent to explore Pluto, is going to continue its trip, out of the solar system. It has investigated one other object in the Kuiper Belt, but the farthest objects we've sent are the Voyager spacecraft, and only one of them they have considered to have entered interstellar space, and that's still just not far outside of our solar system. And it'll take us thousands of years to get to the nearest star at the speed that the Voyager spacecraft are going. And we're not capable of light speed. And so if you think about it, if you had a spaceship that was capable of traveling at the speed of light, it would take you 13.7 billion years to get across the universe. And I don't know of anybody who can live that long. So it's immense. It's humbling. I think astronomy I'm not an astronomer, I'm a mathematician and a physicist, but many of the astronomers that I've worked with on the Kepler mission say it's one of the most humbling experiences when you look out upon the vastness of the cosmos and you realize how tiny we are. I would commend to the student who asked the question and those who have similar questions to go read the prose from Carl Sagan, who is an amazing astrophysicist, and read his prose that he wrote about the pale blue dot. And that image is humbling in itself. And it was an image taken by the Voyager spacecraft. It was completing its primary mission and was getting ready to exit or go beyond the orbit of Neptune and Uranus and beyond Pluto. And he had the idea of turning the spacecraft around and taking a family portrait of our solar system. And you can see this tiny little piece of a speck hanging in what he called it a mote of dust hanging in a sunbeam in the distance. And that photograph represents just 3.4 billion miles, not light years, just miles. And we look like nothing. We look like nothing from that perspective. So astronomy is a humbling experience when you realize how vast the cosmos is.
I think with the progress of all these missions going forward, we will come to know one day that how big it is and what are interstellar space that we have and what is waiting for us to explore. The second question is about what are the mission challenges that are addressed in the recent SpaceX and NASA launch, that is Dragon capsule?
What are the challenges?
Yeah, what are the mission challenges that are addressed in SpaceX and NASA launch?
Well, it's not new that NASA has partnered with private companies in the past. Matter of fact, since the beginning of NASA, we've always worked with aerospace companies to help us build our rockets, our space stations, our capsules. And Elon Musk with SpaceX is a new entrant into that. And competition is always good, isn't it? Competition is always good because it forces you to do better. And this is what SpaceX brings to the table. It's, I think, one of the challenges that it lays on the table for a number of the contractors that NASA uses is that there is another competitor on the block now. And NASA is always about efficient use of our funding. So we now have another option for us to get into space. Of course, Elon has his own objectives. If you read what he's has been writing and also listen to what he's been saying, you know, he has an objective to get to Mars. And I think, you know, NASA is, of course, we continue to team with him. We buy his rockets now, and we also work with him in the design of Crew Dragon to make sure it met all the safety requirements for our astronauts. Just as we're working with Boeing to make sure that their capsule meets the safety requirements of our astronauts too. Elon has other objectives as well. You know, he wants to build his Starship. He wants to get people to Mars. He wants to colonize Mars, and that is a difficult proposition. But we intend to work with him because NASA has an exploration and scientific basis for what we're after, whereas Elon is more, as of course, he has a commercial objective, but he also has a keen idea and a keen appreciation for the science exploration notions that NASA is interested in. But the challenges still remain, how can we do this more cost effectively? And this is what SpaceX brings to the table, because this forces us to not just the other companies that are out there that are competitors like Boeing and Lockheed and Northrop Grumman, but it makes us all a little more willing to accept the challenge of how can we do this more cost effectively and also do it more efficiently.
The next question is more interesting to many of the users, and the thing is, UFOs and extraterrestrial intelligence has been a subject of discussion for a long time. So what are the findings, or is there any trace of UFO in the space?
We get this question quite a bit. It's, of course, the objective behind Kepler was to find Earth-sized planets in the habitable zone of other stars, because we want to understand from the perspective of life itself, you know, what is the possibility of another Earth being out there? And some people would argue that's sort of a humanocentric version of how we view the cosmos. It could be arrogant, because we think that life should be like us. But you look at the abundance and diversity of life on this planet, and we are carbon-based. And you look at how much life on this planet is carbon-based, and of course, we're making that assumption going forward as well. I'll come back to the question on extraterrestrials. I just want to talk about life in general at first. And so when Kepler was devised, you know, there was some questions from some in the community that says, well, maybe, you know, there's life arises on other planets that are out there that are not necessarily like Earth. Even some scientists said it could be based on something like silicon or boron. It's like, I don't deny that possibility, and a lot of scientists would not deny that either. But we use our home base as sometimes as a template. We proceed from what we know to understand the unknown. We know what life is like on this planet, and we anticipate that it would be carbon-based when we look out upon the cosmos too, because of the way that carbon combines so easily with hydrogen and oxygen. And we see that in abundance when we turn our telescopes and look out on the heavens. Now, the question of UFOs, I've never seen one. I've never met an extraterrestrial. I think I would like to. This is sort of dramatized in a movie called Contact. Have you ever seen the movie? It's intriguing. The character playing that movie by Jodie Foster, I've actually met Jill Tarter, because she's playing a character that's based upon the lifetimes of Jill Tarter, who along with Seth Shostak, have been very intrigued with the search for extraterrestrial intelligence. And the questioner, I encourage them to go read about the Fermi paradox and understand what that means. Lately, there have been more reports I've seen in the news occasionally on some of the media forum about we've seen another UFO, and with people who you expect to be credible sources like Navy pilots and seeing things they don't understand. But we haven't gotten to the point, I don't know of any evidence that points to what we call close encounters of the third kind, which is actually real contact. We just don't have that. And I know that if you're familiar with Neil deGrasse Tyson, he gets this question a lot. And he jokingly responded to the questioner one time who brought up the question or brought up this thought that some people have been abducted by UFOs or spaceships or whatever. And he said, well, the next time one of you who's been abducted is up there on an alien spaceship, distract him and get his ashtray and bring it back. That would be bona fide evidence that there's some extraterrestrial life out there. Let's look at it from a different perspective. And I think there's another way to think about this. There's a questioner earlier asked about the size of space. And 13.7 billion light years across. In that observable universe, we estimate that there's 300 sextillion stars. That's 300 with 21 zeros behind it. Our star, our host star, is the only planet or only system around which there's a planet that orbits around, and only life is evolved and on this planet alone. Mathematically, I find that kind of disturbing. You would think at 300 sextillion stars, there'd be other stars out there that have planets around them that harbor some kind of life. But the distances are so vast. Would we ever be able to make contact with them if they were even within our stellar neighborhood of 50 to 100 to 1,000 light years away from us?
I think a lot we have to explore, and then some of the unanswered questions will be answered future. And
Yes.
the upcoming generation has to take up the hat, and then they should come up with these solutions.
Exactly.
So the next question is, how did you make it to the position what you are in, and what challenges did you face, and what interesting things that you have learned, and do you have some message to give it to young generation, that is aspirants of space and of course the aerospace community?
Well, it's in general, I give this advice to students because I've been where they are. It's take advantage of every educational opportunity that's afforded you if you can take advantage of it. Never lose your sense of curiosity. Also, they're making friends today, and they're also developing relationships with professors or mentors or someone who's mentoring them. And that network, if you take care of it, will serve you well for the rest of your life. Always maintain your contact with those that, one, have made an impact on your life. Networking is important because you never know when the life that a life cross path that you meet today will come back and visit you in the future. It's happened for me a number of times. And particularly in the aerospace world, it's a tight-knit community and people know one another, even though it's growing and growing and growing. But I've mentioned this to students in other venues. It's know who would you want to emulate? Who are the leaders that you see out there? Who are the ones that you think you could really learn from? And even among your peers, you can learn from them as well. Everybody who crosses your path in life is someone that can provide you an educational opportunity, and never turn that down. There's everyone you can be a teacher. I gave a commencement address at a university a few years ago, and in those addresses, you get like 10 or 12 minutes to talk to thousands of graduating students and all their families and friends who are there. And I thought about, what do you tell these students? What do you tell them? Because they go to these commencement exercises, and they generally hear this refrain every time. It's live your passion, take some time for yourself to be happy, but also be reflective on who has helped you get where you are. And I decided that day to recognize a teacher I had in high school. He was my physics teacher. He taught high school physics for 50 years. And I remarked about how many lives that teacher affected with all the students who came through his classes for 50 years. He obviously loved what he did. So find something that you're passionate about, but also find something that gives you the opportunity to give back. And that teacher gave back more and more all the time. And it was a surprise to him because he didn't know that I was going to do this in this audience of 10 or 12,000 people, to recognize someone, not just because of as someone who could be a role model to the students who were graduating that day, is now those life, also maintain your networks, and also never take advantage of the opportunity to do something for someone who is less fortunate than yourself.
Yeah, next question is about what kind of programs that the NASA generally offers to students to be part of it, like competitions or any internship opportunities or techno exchange programs.
Okay, yeah, there's there's opportunity for international interns as well. I suggest you Google that. I don't have the website, the link right in front of me, but you could look at for national international interns. There's opportunities, and if you follow NASA.gov, there are a number of listeners. Sometimes we run challenges all the time, and matter of fact, we do a lot of crowdsourcing, which I love. I love when NASA does this, because we're reaching out to best ideas, not just within NASA, but the community out there always has great ideas sometimes too. And we will issue a challenge to a lot of universities, asking them, share with us your best ideas, and we always put prize money associated with that, so that we can give a little incentive and motivation for participation. But those are the kind of things I would look for. Just follow the nasa.gov website and look for the challenges that we issue periodically. And if they're interested in being an international intern, I would also just recommend that they look at that particular link that talks about how to become an international intern at NASA.
Yeah, if you don't mind, we'll take a couple of more questions.
Okay.
Okay. So what are the challenges with deep space communication, and how to tackle them?
For small spacecraft, it is a challenge for us, and it's one thing we're working on. As more and more missions get created and also get fielded and also get operated, of course, you get to the point where for NASA, our deep space network becomes overloaded, and we're looking at optical comm as a means to help with that. But of course, one over R square thing, it's the same thing, even with RF. And so we're looking at ways, how can we do optical comm from deep space distances? And that's a challenge that we're working on right now. Doesn't mean we solved it, it's a challenge. RF works for us because that's how we communicate with Voyager, even at the depths of space, but that's a very low data rate when you think about it. And of course, the further away it gets, the lower the rate. So if you have a great idea, if you're a science fiction fan and you watch like Star Trek or some of those other things, they had something that was fictionalized as subspace communications. It's like, what is that? There was some sort of Framsatron that had apparently developed in the future, which will allow them to do almost instantaneous communication across light years at faster than the speed of light, if I understood their technology. But that's a fiction. NASA deals in the world of reality and facts, and we're finding this a difficult thing to deal with, because everything we have sent into deep space, our communications have been RF, and of course, the further out you get, the lower the data rate and signal strength and capabilities you get as well. So if one of the students has a bright idea to take us to the next generation of communications, bring it on. We'd love to hear about it.
So how viable is to demonstrate the quantum pairing or the quantum communication in terms of deep
Ah,
space network?
yeah, we're working on that. As a matter of fact, we have a quantum computer at NASA Ames Research Center where I work. NASA Ames Research Center is the home for NASA supercomputing capabilities. And we have, I think it ranks 10th or 12th in fastest supercomputer in the world. It meets our needs, but of course, Google, with its services, they're building a new Googleplex next door to us. And NASA is collaborating with Google and Microsoft. And you may have heard a news announcement in a not too recent, in a recent past about a feat called "We've Achieved Quantum Supremacy." I'm not a computer scientist, so I don't quite sure understand what that means yet. But it was an experiment that was conducted by NASA with Google and Microsoft, in which this effort was using the NASA Ames quantum computer that we have, and also a couple of quantum computers that Google has, to achieve something called quantum supremacy. We've also started looking at what does quantum communications mean. Is there a way that we can quantize communications to allow us to transport even more information? I am not well versed in that area. I just know there's certain people in NASA that are working in that area. And if I ever get to the point where they think they have something I can put on a very small satellite, I'm going to talk to them, see if we can demonstrate it on a very small spacecraft. But it's something that is intriguing, and I think there's a lot of brainiacs out there that are working on this. But unfortunately, I'm not as well versed in it as I'd like to be.
Okay, so how practical it is to have a interstellar travel, and then of course the nuclear space propulsion uh, coming into the reality?
Well, let's talk about the second one first. Let's talk about nuclear propulsion. NASA's investing in that. And as a matter of fact, if you look at the nasa.gov website and you look for the Space Technology Mission Directorate, that's the directorate I work for under small spacecraft. There's a number of investment activities going on in that area, and one of which is nuclear propulsion. NASA's interested in it again. But for interstellar travel, we're not there yet. All our propulsion systems are still chemically based. And I know you see these intriguing articles that show up in certain media sometime to talk about interstellar travel. And of course, in Star Wars and also Star Trek, they're capable of doing that. But that is still a fiction. Someone needs to tell Einstein he was wrong before we get to the point. Maybe there's one of these students out there listening today, maybe they're the next Einstein, and they're going to figure out a way to get past E equals MC squared. So we're a ways away from that. But if you want to look at something that's really intriguing when it comes to getting up to these light speeds, go look at the Breakthrough Foundation and what they're working on, something called Breakthrough Starshot. And it's the acceleration of these microchips that they would throw thousands of these into space, and they would hit them with a laser farm from Chile to accelerate them to sublight speed, about 1/5 the speed of light, in anticipation of trying to get them out to the planet that is allegedly orbiting the Alpha Centauri system. And they would like to do a flyby of that planet using these microchips that have this large hole around them that would be accelerated using a laser farm that would hit them and get them up to sublight speed to make that trip. That's just, and that's, they're still, I think, many years away from making that happen. I think they're still working on technology, but light speed we're just not there yet. We're hostage to our chemical propulsion systems right now. It's the most reliable thing we have. But once again, if we have a student out there who can invent something like that, I'm sure you make a lot of money.
Definitely, definitely. I think the future innovations is the pathway to larger space exploration and to address
Yes.
these challenges. I think we have a lot of questions more, but I think in the interest of time, the questions will be answered in the subsequent sessions. And of course, we can always communicate with Mr. Roger Hunter on different forums. And thanks for accepting our invitation. And it's been an enlightening session for all of us. To just to enlighten, a lot of invitations have come to join this session, and then a lot of registrations from the students, faculty members, and aerospace professionals. And it's really interesting, and you have given us a lot of insights about Kepler missions, and of course the new programs that what NASA is actually going to take it forward. And thanks for accepting our invitation and making it possible. It's such a interesting and interactive session.
Thank you. I've enjoyed it.
Okay. Thanks everyone. Thanks for joining this session. And we would like to thank everyone who has joined this session. And I hope it has been interesting and interactive to all of you. And nevertheless, I think we should continue our innovation and progress in terms of science and technology. And we should address these space challenges, and we should progress as a humanity and mankind. And thanks again, Mr. Roger Hunter, and signing off from UPES. And thank you. Thank you.